So this morning we have a session about correspondence analysis for ecological data. And we have two invited speakers. The first one will be Cajo J.F. He's the author of a seminal paper which has been cited by Michael Greenacre in the introduction of the conference as a key paper in the history of correspondence analysis. So let's start with Cajo J.F.
Good morning, everybody. I would like to thank the organizers for giving me the opportunity to celebrate this anniversary with you here in Rennes at Carme 6, because canonical correspondence analysis is really my scientific baby that has now grown up. I will present a very personal history of the thing, mixed with slides in light blue that show the way that I teach correspondence analysis and canonical correspondence analysis to biologists and ecologists. The papers that I will be referring to, as far as it's mine, are on my website, even the ones that are in obscure more obscure journals. So what does the abstract say of this paper that we are actually celebrating, or I'm celebrating with you? It said in the abstract that it's a new multivariate technique to relate community composition to known variation in the environment. It says that it extends correspondence analysis, and that usually in ecology correspondence analysis was applied in two ways, namely in two steps, because first species data were analyzed and then the excess of correspondence analysis were interpreted in terms of the environment. And I changed these two steps into one step, the CCA. And then an important thing is, of course, what comes out. And one thing that comes out is an ordination diagram. I forgot here, of course, to say that I have two important subtitles of my talk. It's correspondence analysis without chi-square and le principe barycentrique as ecological niche model. Of course, how are you going to introduce it? You can't give you as long introduction as I do. So the shortest introduction to canonical correspondence analysis is that it is correspondence analysis with external linear restrictions on the row points. It brings the power of regression analysis to correspondence analysis. And the same holds, it's general enough to be applied in a multiple correspondence analysis framework, and it's really a simple generalization then of a simple case of homals. At the same time, we are celebrating, of course, the conception of the same method, because at the same time Daniel Cecel and Jean-Dominique Le Breton, they dreamt up the same method, and here I show three words: schéma de dualité, propriété optimale, and an illustration. And here you see that ACC, of course you have to do it the other way around in French, right? Is as a discriminant analysis, canonical correspondence analysis is as a principal component analysis, and it's as a double coudage sous constraint linéaire. So you see there's really nothing new around, and nevertheless it had quite some impact. So one of the duality diagrams is being shown here, and I show another one as well. That same year, I also had a second paper on the subject, and there really this weighted averaging comes in as a separate method. So not correspondence analysis as the basis, but weighted averaging. So that's where the principe barycentrique comes in. And then we have two more papers by Jean-Dominique Le Breton and co-authors on applications with quantitative environmental variables and with oh, sorry, I should use the mouse. And qualitative environmental variables. Okay, I said it has been a big success, so I'm very, very glad of it. 3,000 citations to the 3 papers that I wrote on the subject, so not too many actually. And I can also say that what I'm presenting here is the second time in this 25 years that I'm presenting it to a statistical audience. Here you see a screenshot of the canonical, and on the left-hand side, vertically, the number of citations, and horizontally, the years taken from Scopus. So it runs from, say, 100 to 300 a year. And then you see the uses the use and most of our ecological fields. But then there is a little square here, which is other. And of course, that refers to all kinds of citations in either soil science or psychometrics. What is the kind of data it was being designed for? And this also introduces some notation. So I will have species data, which is my matrix Y, consisting of n sites, which are the statistical units. It are pitfalls in this case, in which some spiders fall. So we count the number of pitfalls, of number of spiders that fall in such a pitfall. And there are 12 different spiders, and each of the pitfalls is on a site, and on the site you can measure all kinds of environmental variables, like water content, the percentage of bare sand, and things like that. Actually, you see that ecologists, like genomics people, they put the variables in the rows, because then you can spill out, really set out the names there, and in the columns, the statistical units. So I put it there then that Y transpose is actually this matrix. So what is then canonical correspondence analysis? Yeah, I said it in one sentence, but another way of saying it, and to make it more difficult, of course, and please read it, it also sets down the notation, is that it solves some kind of eigenvalue problem. Okay, who cares, right? So the eigenvalue is being done on matrix Y, which are really response variables, the abundances, so the amounts of species in sites. And the other matrix is the matrix Z of quantitative or nominal variables. It's the predictor matrix, and it's, in my case, the environmental variables. And here is the eigenvalue equation. It always looks awful, right? But if you know canonical correlation analysis, you will not be so surprised, except that this D sub C and D sub R, they look a little bit funny in terms of definition, because they are really diagonal matrices with on the diagonal the weights, the row totals and the column totals. If you are clever, you can also see directly 2 special cases, namely that Z equals the identity. Then it boils down to correspondence analysis, and you can also see when Z is an indicator matrix, just one indicator matrix, so one nominal variable, then it also immediately is a canonical correspondence analysis. So, and this was then the first ordination diagram, the factorial plane, if you like. And it contains 3 entities: species, site, and environmental variables. And you see that the environmental variables are presented as a biplot, and because each of these environmental variables represent an axis. And if you project all the species points on this axis, for example here on bare sand, this variable, then the projection point show the approximate ranking of the species centroids along this environmental variable. So really that's, again, centroid, center of gravity, barycentric principle. And the other, so I list here what is that the X and the U can be the side points, and the species point can be interpreted in the normal way as in the correspondence analysis, and the U and the C together form a weighted least squares biplot of something very peculiar, the weighted average of species with respect to environmental variables, but I will show you what it actually means. So the history of canonical correspondence analysis is, of course, the history of correspondence analysis in ecology. And it builds on theory. A plant species does not grow when it's either too wet or too dry. So we have Liebig's law already from 80s so many that says that a species requires a particular amount, a minimum amount of a resource, nitrogen for example. And that's what we use in agriculture. We are at the agriculture university, you certainly use Liebig's law. But there is also another law, you should not give too much, because a species does not tolerate more than a certain maximum. So that's called Shelford's law of tolerance. And made a little bit more quantitative by Hesse in 29. And then you can draw a picture like this. That's horizontal, we have the resource axis. Vertically, we have the abundance, and then, just the probability of being present. And then we have these single peaked curves, which I call unimodal curves. And the essential thing is that niches, what is an ecological niche? You have two of them, the fundamental niche, but what I'm interested in is the ecological niche. That's the region where the species actually grows. And the important thing why correspondence analysis and canonical correspondence analysis works in ecology, in my view, is that niches vary among species, and that's what I will really use. This is, of course, related to preference models. In marketing, it's with our textual data analysis, we have words get into fashion. So if we take on the horizontal axis time, then first a word is not being used, then it gets fashionable, and then it gets out of fashion again. And words differ in terms of the times they get their main exposure. The history of correspondence analysis also built then on a method which is based on this simple model, namely the method of weighted averaging. So the preference value of a species, or the indicator value of a species with respect to a physical gradient, for example moisture, is the weighted average of moisture values at the site where that species grows. And in reverse, the estimate of moisture of a species, when you know something about the species, is also a weighted average. So this has been well developed by these famous ecologists. And in 73, Mark Hill, he had the idea to iterate this process, these two methods, to replace the manifest gradient, so for example moisture, by the best latent one. And this is, of course, reciprocal averaging, which is the same as correspondence analysis. So it's really le principe barycentrique both ways. Independently, and I didn't really ask Maurice whether he was using also the niche model, but the first application in ecology is Roux and Roux in Revue Statistique Appliquée already in many years earlier. So this is my blue slide. So how do we estimate such a weighted average? So here on the vertical axis we have again abundance. We have abundance here, and here we have this physical gradient moisture, and we have, for example, 200 sites, but only at 6 of them we have a positive amount, and for the rest it's all zeros. And then the weighted average is like this. Okay, so if the particular species is found at just three sites with moisture values 20, 30, and 40, then I can work out by head the average, which is 30, and of course my formula gives that as well. Here it is a straight average if I just consider the ones, but if I consider also the zeros, the absences, then it's a weighted average, namely weight 1 for a presence and a weight 0 for an absence. And reversely, if I know from some literature the niches, the optima of niches of 200 species with respect to a physical gradient, for example moisture, and they are on a scale from 0 to 100, then I can estimate the moisture value at a site when I know the species composition. So for example, let a particular site contain species which have these optima. Then we have just presence absence. What is the weighted average? It's just 80. And if we have some amounts attached to it, then of course the weighted average will shift a little bit to the left. Really, we should do some exercises on it because it looks quite simple, but it is not so simple. Because there are some things that we really need to understand. Namely, for example, that this optimum has the same physical dimension as the physical gradient, right? So if moisture has a particular physical dimension, then this optimum as well. It's on the same, expressed on the same scale, and that should hold always throughout your formulas. So the idea of Mark Hill then was to iterate that, and I represent here this iteration scheme. Would you just derive a new species score for initially arbitrary initial scores, and from those we derive new site scores as weighted averages of species scores, remove arbitrariness, and then we go on until convergence. So that leads to the transition formula. You have to do some mathematics for that, of course. And here I represent them. Eigenvalues between 0 and 1. But what does it optimize? Just for comparison, principal component analysis is really this set of equations if you put it down there. And most people would represent it in some kind of strange eigenvalue manner. But then it's really not reciprocal regression, but two-way weighted summation, rather than two-way weighted averaging. But what does it optimize? What did we know at that particular time? We knew that correspondence analysis can do very well in seriation. It can recover disordered Petri matrix, and I show here the ordered form, namely that we have consecutive ones in every row. Look at Heiser 81, for example, and the full. This matrix was, of course, much earlier. I think by Kendall it was proved that it could do this way. Then we have things like the relation with canonical correlation. You know all of that, but I never understood the importance of this particular optimization thing for ecological purposes. Then the third point, it finds block structures in two-way data. If I have here 4 blocks, and they contain zeros and abundances, but all off here and here are just zeros, then correspondence analysis just gives 5 eigenvalues equal to 1, and they separate completely these blocks. This is still very useful and being used in spectral clustering, which is a very popular topic nowadays. But on the other hand, it's also known to have very bad features. Correspondence analysis is very sensitive to rare species. That's really the case that one of these blocks consists of a single species and a single site. It just will set that one apart with a very high eigenvalue. And then it has this famous arch effect or Goodman effect, and please trust me, never call it a horseshoe. Because it's not a horseshoe, it's not bended in. That would be a false way of describing the thing. And for that, ecologists devised a method, and Mark Hill in 1979 developed his program Decorana, and Hill and Gao presented that in Vegetatio in 1980. Okay, so how was then canonical? So this was about the state of how I saw the whole thing when I was working. Here I describe a little bit of it. Ben s'écrit de l'analyse de données, volume 1 and 2, were on the shelves of my colleague Hans van Biese. And so I saw the nice picture of Huygens on the front, and I did a little bit of reading, but I don't know how much influence it had. Can't really remember. Then I went for an MSc in statistics in Newcastle with Peter Diggle, and the head of department was Robin Pleckett. And I learned maximum likelihood equations for exponential models and things like that. Actually, in a period that GLM was already invented, but it was not presented in the new fashion. It was presented in the old fashion. And perhaps that's really what is important for this talk. In that period in Newcastle, I was in contact with Colin Prentice, who did a lot of non-metric multidimensional scaling, and with Mark Hill, which I already introduced. And I was doing a paper, not during that year, but I had it on my desk for principal component analysis biplots, because one of the professors in Wageningen, Professor Korsten, he was really into biplots together with Ruben Gabriel. And I had a paper on my desk with what I was working on, principal component biplots and diversity. It appeared. But then Mark Hill said, I don't like it at all. That's good when you come there, right? I really dislike your paper, because ecology is not linear. And differences in niche location, that's really differences in environmental condition, different niches, that's really what creates between side diversity. And you can't grasp that with your awful linear model. 81 was the second GIFI course. I attended that, and I benefited a lot from it. Good context with Jan de Leeuw and Willem Heiser. And from that period, so mainly by the stimulus of Mark Hill, I studied for ecologists in different projects the properties of weighted averaging compared to maximum likelihood, because that was really the group I was in. We do regression and GLMs and things like that. And what are now the properties of this very strange method of weighted averaging in ecological niche models? And then combining that, reciprocal averaging, etc. When might weighted averaging be as good as maximum likelihood? And I don't think I have really time to go through this, so I stop. So you see that weighted averaging might do very bad. So here's the true response curve. Here is the sample distribution of my moisture values. And whereas initially B had a higher optimum than A, then now it is reversed. So for this marginal distribution of X, the optima are reversed. So be warned. Then I was I was very brave, and I posed the problem the other way around to find a model such that actually this method, this weighted averaging method, is optimal. And I proved that using the Cauchy-Schwarz inequality in this particular paper, and this comes out. And then you combine things in correspondence analysis, and that's by Biometrica paper. So if you want to refer to niche models and correspondence analysis, please cite this paper. So how was then canonical correspondence analysis derived? I was preparing with Colin Prentice in Uppsala in '84 a theory of gradient analysis. So gradient analysis are these values of moisture and things like that. And we were looking for something like canonical correlation for niche models. So then we had, at a particular night when I was just going to leave, the real idea, let's do linear constraint on scores in Gaussian ordination and approximate the ML equations just as I did for correspondence analysis. And later then, of course, you get the more usual stuff, which I will represent in the next slides. So very quick first draft and some computer programming extending Decorana. Report was sent around, and Jan, for example, gave a whole new derivation in Homals terms, and he commented, as you can see from this derivation, canonical correspondence analysis is a relatively simple special case of Homals, or if you like, Carnals, and I can just simply agree. And this suggests directly which geometry GIFI would use. We never went really into that together, so perhaps I have a chance to do that now. Nothing bilinear, nothing biplot, just centers of gravity. I say yes, certainly for nominal predictors, but not for quantitative predictors. And I extended this Decorana to Canonical to include, oh yeah, so in that time in '85, I developed a method which I baptized canonical component analysis. Canonical correspondence analysis, canonical component analysis. But then, of course, people were wise enough to say to me, Willem Heiser, but there is some guy von der Wollenberg, redundancy analysis. And he should have, of course, cited Rao 64. But I developed the equations myself after I developed the equations for canonical correspondence analysis. So with help from Onno van Tongeren and Petter Smilauer, we developed the various versions of Canico, and the real success is not on the diagrams, but really on the permutation testing, in which I put a lot of effort to do that in the correct way, and developing approximate permutation methods in regression models. And then, you know, I don't do very many conferences, talking here for the second time in a statistical conference on it, and I really had my ambassadors to do the real spread of a nice idea. Then we developed partial canonical correlation, because that's important if you really want to do partial regression coefficients. And I presented that. That was the first presentation for a statistical audience in the first IFCS in Aachen. And Yves Escouvier stood up, and he was very strong, and he really disliked it for two reasons. First, the name was totally wrong, and for the second reason, that of course he had doubts about this real regression stuff. And we can be sympathetic certainly to the latter. But immediately he invited me as well, so it was really a good way. Invited me to Montpellier to work with Jean-Dominique Le Breton and Daniel Ciesel and Paul Sabatier, and who independently invented this CCA just a few months after I did. So they did it, I believe, from Jean-Dominique Le Breton in February 85. So in that period, I tried to bridge the gap with the French, because I lectured in English, but with only French references. I learned about duality diagrams, and much later I found R.H. Green in ecology. It's well known, he has written several books, 71, 78, and there he develops multi-group discriminant analysis. And it's really CCA. So, of course, correspondence analysis is nothing but canonical correlation analysis, and it's nothing else than CCA. So what the hell are we doing anyway, right? But curiously enough, the interest in this method was lost at the same time. You look at the dates that Mark Hill got popular with his De Corana. So we can actually celebrate, as the biplot, 40 years of canonical correspondence analysis. So how do you then get, with all these papers around, to say how does this work? Okay, here we have things against moisture. And then you go to coffee break, and I said, I have this data set, and I think moisture is very important. But then somebody else says, that can't be true. It should be nitrogen. And so how are we going to judge which one does better? So we have to have a criterion of fit. Of course, you know this as a statistician. So the idea was to calculate all of these weighted averages, and then to compute the dispersion of the scores, if you like, the variance of the species scores, with respect to a standardized environmental variable. And so then you have a measure to say, okay, nitrogen does better than moisture or not. And if you are this far of having a nice optimization criterion, then you can replace, first of all, you should immediately recognize that in terms of discriminant analysis, this is a way of saying the between group variance against the total variance. If you have such a criterion, then you can let your computer search for the variable, the latent variable that does best. So it optimizes this dispersion delta. It separates the species score as measured by this delta. Actually, from this derivation and just how this works with this delta and this separation of these optima, if it's a very strong gradient and you clip it down here and you flip the axis, you have a folded axis, then you can see that this folded axis has also a very high delta squared. It also still separates, namely, all the species that are down here and the species that are down there. That's a simple, non-mathematical description of the arch effect. So canonical correspondence analysis just adds this linear constraint to the whole business. So it's really the side scores that are linear combinations of environmental variables that best discriminate the species scores curves in terms of this delta. And in terms of the multigroup discriminant analysis, it's really between divided by total. And then we have the algorithm of CA, and you just add one extra step. Of course, weighted multiple regression, why these weights? And these weights are also in this thing I started with. So how do we get to those weights? Why would I be certain that it should be certainly those weights? Because also in the delta criterion, I can do different standardizations, and we end up with something else. So that's where my correspondence analysis paper came in well in biometrics, because we do precisely the same trick, except that we now say, okay, in my Gaussian model, I have now my latent variable is really a linear combination of my external variables. So this is what it describes. Just as CA, but now with linear restrictions. So here I have actually the derivation. I keep it for a second. Then from this approximation of these ML equations, you immediately get to these transition formula. So they came first. And to express them in matrix algebra, then you have this set. You may be more familiar with such type of scores. But perhaps you don't do transition formula, and you only look at eigenvalue problems. Okay, how do you derive eigenvalue problems from such a set? Okay, let's start with this one. I have it down there. Oh, I have an x star. X star is given. Let's insert it. Oh, I have a u. Oh, u is given. Let's insert it. Oh, x is given. Oh, let's insert it. Okay, and then I have my nice eigenvalue equation. Nothing difficult, nothing secret. It's pretty standard. Here is one of these duality diagrams that I worked on. This is from the presentation that I gave in Montpellier. And to be honest, I don't understand duality diagrams after so many years after studying them. At that time, I understood it. But what I did understand much better was that each of these arrows actually corresponds to one of my eigenequations, of my transition formulae. So I have them here in lines. And then the other thing what was popular with, certainly with Yves, was the PCA triplet. And here I have some of them. And they define the least squares properties of my ordination diagram. So the ordination diagram may contain two sets of scores. We have namely two, but we of course don't. One set of scores derived from the environmental data and one derived from the species data. The latter is closer to Y and the other one really underlies the eigenequation. And so normally I plot x star and u, certainly in the initial papers, and I plot the things that are related to the interset correlations. I don't plot this b, of course, because that's a regression coefficient, and it can be very unstable with collinear predictors. So instead, the score c for each of the environmental variables is optimized in such a way that it gives a weighted least squares approximation to the center of gravity of each of the species with respect to each of the environmental variables. Of course, this has not much meaning for nominal predictors, so that they're really where it is, again, a centroid, a center of gravity. So here is another example in the second paper, just to show actually that the predictors can, of course, be both quantitative and nominal, and that we certainly, with partial canonical correspondence analysis, we can use all powers of regression. So here I have then such a biplot. So to look something up for manure, we'll make a line of it. We project each of the species on it, and everything in the biplot, in this plot, is now a center of gravity. So the projection points of the species are the center of the site projection points. And I like this kind of way. And here in this plot, I have then the class centroids for my 4 classes of my single and nominal variable, although they are also centroids. Doing CCA in R, you can do it with Anacor very nicely, because it can give also these confidence ellipses. But you can also do it in vegan and in ADA4. And in vegan it's nice, at least that's what I know, because that's normally what I use then for teaching, is canonical CCA there with really a formula interface for the whole business. So what about the relationship with RC models and ideal point discriminant analysis? Here's really some of my headaches for the last 25 years, because you have both this bilinear model and this distance model, and you really understand why they are equivalent. You can really understand why they are equivalent. And just add linear constraints, and you get everything. And so perhaps I would like always to do it like this, perhaps even with in a mixed model framework, and we really get very close to the current work of Marc de Roy. So look at his paper that I here show. But in terms of history, it's interesting to see that I show that CCA is an approximation to this model. Okay, we know that already, but what I want to stress is that Goodman also showed this for small lambda. Why for small lambda? Thank you. Because really he uses this idea of doing a Taylor approximation of this model. I mean, that's Taylor approximation. I mean, that works only very close to independence. That's where the one-dimensional reconstitution formula plays a role. But in my models, how can that be linear in such a way? So we later landmarks are really co-inertia analysis from Daniel Cessel, Sylvain Dolidec. And perhaps I should notice the forward selection. So these are actually also CCA PLS are really methods to take account of the thing that predictors can be very collinear, and if you have too many of them, there are effectively no constraints, so it really reduces to correspondence analysis. You don't want that. And so you have to do something about it. Three ways of going about with it. You do either forward selection, so or you do you disregard any of these correlations, or if you do a PLS type of approach. In the appendix of this paper, I carefully write down how this should be done, just as you compare correspondence analysis with principal component analysis. There are two essential steps, namely pre-transform and post-transform. And if you leave out one of these steps, you're out. If you apply this, so I can also add a new technique here, because I'm very fond of Michael and Arthur Tienenhuis for the regularized, you read the name here, and he will present that this morning, I believe. And so just insert these methods, these transformations, pre and post, and you can use his package to do all these kinds, which give methods in between CCA and CCA PLS. Then we have an important variance partitioning paper by Braak and Legendre. Then we have double constraint correspondence analysis, so the RLQ framework. And all these CA methods are obtainable from standard methods by inflating data matrices. Nothing new for me if you're aware of the super indicator matrix used in HOMALS. And in ecology, you can say, okay, rather than taking as unit the site, which is really the statistical unit, I take as real observation the individual, or the site-species combination. And for that one, I use a much bigger, so I inflate my matrix with this as unit, many more rows and many more replications of the same value, but that gives always the correct answer, or by the pre or post transformation. I put in here the question mark because as soon as I did it, I should also say that I developed co-correspondence analysis. I presented that at 2 Carme conferences ago, and that doesn't work like this. So in ecological terms, we have quite some number of methods. Here I list whether we have response variables, so community data, or whether we have predictors. So for example, environment, but sometimes you might wish to invert their role. And here on the listing, we have co-correspondence analysis. I want to conclude with my the thing that I was already telling about, namely, to me, correspondence analysis is a chameleon. It sometimes shows up as a linear method in the reconstitution formula, and then we can safely always call things biplots of row and column points. And that's really the way that most people, because it's hard and fast, nicely these squares. And then the other way, for unimodal models, we have this relation with multi-group discriminant analysis, so that's also hard and fast. And there we have then this row-column distance plots. In the RC model and log ratio analysis, you know perfectly how these two go from one to the other, from the what looks bilinear on some transformed scale and the other model. But of course, with the reconstitution formula, it's very bad with an arch effect. So Michael Greenacre, yes, a reference to Michael. He has a very interesting paper on power transformations in correspondence analysis, and he could have cited my work. There's no citation. But if you look carefully, for all statistical journals, I say, Y is Poisson, and I've counts. So I analyze the thing untransformed. But when I do things for ecological papers, I say, okay, my weights get far too disparate, far too much weight for particular species. And I take log Y plus 1. And here, that's where we agree. That's the paper that really explains that it does much better in removing arch effects and things like that. So some final remarks. I think there is room for sparse canonical correspondence analysis and the idea of applying principal response curves in a CCA context. And that's really a method I didn't, it's good for a display of main effects. Thank you for your attention.